Hello, this is a talk on open world AI here from Volition. Today I'm going to be talking about important aspects of AI in open world games. The three main topics I'm talking about is open world response, scalability, and environmental interaction. I feel these are the most important aspects of making AI in open world games. My name is Canary. I started here on Saints Row 2, where I made AI look drunk, and I continued on RFG, doing various missions and activities. Saints Row 3, I re-engineered the AI architecture to run faster and also enable us to do faster iteration over multiple special behaviors. And Saints Row 4, I was the only AI programmer until the expansion, at which point I became the AI lead. But after being at Volition for 7 years, I still feel like one of the new guys because we have a very long history of game making, and a lot of these guys are still around. Just as a refresher, Saints Row 3, or the Saints Row franchise, is a open world third-person shooter, which is an adventure series with a comedic plot and a large variety of gameplay activities. The first topic I'm going to start with is open world response. Saints Row 2, we spent a lot of time making various vehicles and systems, fairly complex systems, which would introduce new enemy types or new NPCs to the world. And it was very reactive to what was happening in the world. When there was a fire on a car, a fire truck would come and put the fire out. When a person died, an ambulance would come and revive them. And when the player was violent, someone would actually pull out a phone and call the police, and the police would show up and investigate the area. And these systems were there to help the world feel more alive and reacting to the player. The other system that we had was notoriety, and this was most of our open world combat. And the basis of this was to increase enemy spawning as the player was more violent in the world. SR2 also had a strong variety of police, SWAT, helicopters, motorcycles, boats, a large variety of vehicles, and these all came in through different algorithms and different means. But in the end, it was pretty evident that we spent more time on the scope of all of these types of vehicles and not necessarily on the player experience. SR3, we wanted to focus more on that player experience, and so we actually lowered the number of enemies and introduced a larger variety of them. And each of these new enemy types was to try to invoke a new behavior from the player himself. Some enemy types would encourage the player to dodge or kite or take cover. And a lot of these were there to, break up the pacing and to provide a different experience, so it wasn't all the same. And this also, so while the SR2 system made the world feel more ambiently alive, the variety of enemy types actually provokes the player to play the game differently and causes them to think, which in the end is more entertaining. The early concept of pacing in the open world was to spawn a vehicle every X seconds until you hit a cap. And then to escalate the fight, you would change the spawn rate or you change the cap. And this commonly resulted in problems that we termed as the trickle or the flood, where you either don't have enough enemies or you have way too many enemies. And this was very difficult to balance on one particular player, but to balance this on a range of players was almost impossible. And even when we could get that work in a good scenario, SR3, we found that there were these very large difficulty spikes. And we found out that these were actually coming from the ambient system. What would happen was the notoriety system would want to spawn say, 6 cops to go attack the player. And meanwhile, the ambient system would spawn 4 cops to go get donuts. And these 4 cops would see the player attacking other cops, and they would turn around and join the fight as well. So now this easy or medium encounter now just doubled in size. And so it is much more difficult for the player, and it's not something we intended at all. SR3, this actually became a larger problem because we were spawning flashpoints. These were static points in the world where enemies would do certain activities, and they would be there most of the time before notoriety or any of the other systems kicked in. So the overlap of these enemies already there and the notoriety introducing more enemies introduced some very difficult situations for the player. Also, we did not intend. So we had to rewrite some of the notoriety system to actually account for how many enemies already existed in the world, and then only backfill the number of enemies that we desired for that situation. SR4, we actually rewrote the spawning system to spawn the enemies in waves. This is very typical of any survival wave game. However, we still encountered some problems because there was enough carryover from when one wave ended and another wave began. There wasn't always a clean cut between the two. So here we actually have a situation that the player's in, and there are 7 different enemies attacking the player, 7 different types of enemies. And I assure you there was no data or designer that intended for this to happen. So there's still a lot of problems that we're looking into, but the actual takeaway here is to look at your spawning holistically. It's very difficult to see multiple systems trying to introduce new enemies, and they need to either have a management layer or some strong coordination so that you can build or maintain a big picture of what is going on. The next problem we wanted to address in notoriety was that after the fight escalates, it tends to just get really, really hard, and it kind of hits a climax and it just stays there. The only way to actually resolve this is to run away and go back to your safe house where notoriety would be cleared. And we really didn't feel that this was the experience we wanted to provide for the player. Running away should not be the end of this huge climactic fight you've been building across the city. So we started looking at, okay, well, obviously we want some dramatic arc here. We want the player to feel rewarded for doing all of this gameplay and being very good at it. However, we haven't rewarded the player for doing this in the past because they were killing cops, and surprisingly, we actually have morals. So Saints Row 4, we had the opportunity to change this to the notoriety now spawns aliens, and we felt perfectly fine with rewarding the player for killing aliens. So that allowed us to change how notoriety ends. It no longer ends by returning to your safe house. Now it actually ends by fighting the capstone AI, the warden. And this is the boss AI that follows a dramatic arc. There's very high intense, very dramatic gameplay leading up to this finisher, which kind of provides some suspense and then some gratification. There's a lot of fancy animations and visual effects and sounds that go into that to make that a satisfying experience. And then the player is very aware that now notoriety is done. He is won. We also found that fighting our 6 or 7 waves of notoriety was a long experience, and not all players wanted to progress all the way through that. They wanted an early out. So we introduced the Golden Sid, which was a high-speed gameplay, high-speed chase gameplay, which followed the same intensity and satisfaction as the Warden fight. So my takeaway there is to really focus on the player experience and rewarding them for actually doing this gameplay. In the past, we had punished them for being violent or doing things we don't want them to do. And turning this around to make it a rewarding experience was a big benefit for us. Another problem we had was Saints Row 4, we added superpowers. Our primary means of introducing new enemies was to spawn a vehicle 100 meters away from the player and have them drive up to you and get out and attack. However, now the player can run 40 meters per second and jump over buildings. So our previous means were completely obsolete. And even once they got into combat, the players, as I said, could run up walls and jump over buildings. So then the AI had no means to catch up with them or to pursue them. So we had to introduce a number of new AI and techniques. The first thing we tried was teleportals. These were destructible monster closets that could be spawned anywhere over nav mesh. And they could essentially just pop in right in front of the player and bring combat to him instantaneously. The second thing we tried was something we termed transmogrification. This would take an existing enemy in the world and play a very in-your-face effect to let you know that something was happening, and it would change him into a more difficult enemy. The third type we used was AI just simply falling from the sky. We used this in very dramatic scenes for the warden entrance. I think we used this for some of the other boss fights as well. My actual thing I want to suggest here is that you try to be creative and find ways to support the context of the game, but also to present the AI to the player in very effective manners and that are also entertaining. So to wrap it all up, I wanted to have open world systems work together and provide a rewarding experience to the player, really focusing on the player experience in systemic systems is very difficult, but it provides a lot of good gameplay. The next topic I want to talk about is scalability. There was a lot of challenges we had in open world games because of their scale. And later you'll see how I tie this into environmental interactions. All right, so next I'm going to be talking about scalability challenges that we faced on the Saints Row series. The first system that I was responsible for was the line of sight system. And obviously this is the number of line of sights you're going to do is proportional to the number of NPCs you have. So at first you might think, well, worst case is 75 people are attacking the player. Or you might think ahead a little bit and say, okay, well, what if you have 3 followers with you and there's 72 attacking them? And then someone makes a mission where there's a large number of allies and a large number of enemies, and you end up with more line of sight checks than the system can handle. So in this particular case, around 1,500 line of sight checks, and we cap it 4 per frame for performance reasons. That resolves in about 12 seconds. So on SR3, we spent a lot of time trying to figure out how to prioritize these line of sights. You know, which 4 of these are most important to our gameplay, and came up with a lot of complicated algorithms that inevitably added more cost to the frame rate to see how long it would take to do these. And on the screenshot, you can see there's the green lines are the line of sight checks that are done. The blue lines are the ones that were deferred to process later. And we're getting delays here between 1 and 11 seconds. So if you can effectively prioritize these, you can cut this down to around 1 second. However, then you cause some starvation in the other AI that is off screen or or a little bit further away from the player, and these AI are very slow to respond or don't respond at all. And this is actually how we shipped Saints Row 3. And there was one more case that got worse. This was one of the later missions that I found out about right before shipping. Was there were 3 teams, all hostile to each other, and this caused even more raycast that the system couldn't handle. However, it was able to do the most important ones, and typically in situations like these, there's enough things blowing up and people dying that as long as the AI isn't just standing there not doing anything, then it's fairly acceptable among the chaos to have some delays. So when we started working on SR4, we really wanted to look at how can we do more than 4 raycasts, because that is a big part of our problem. We need to do raycasts, and we need to do more of them. So the first thing we started looking at was, okay, can we multi-thread these, and can that have a big impact? That was the hope. So we came up with some code that would run 4 of these simultaneously on the Xbox and PC, and I think it would do 5 or 6 on the SPUs of the PlayStation. And this was set up to just get immediate results. This was not deferred. This was just do as many raycasts right now as possible. And this led to actually some interesting systems, which I'll get to later, the flying and the jumping AI, which came out of this fairly unexpectedly. So to kind of review how it works, SR3 would queue up a whole bunch of raycasts over the frame, and then at the end of the frame, it would do the ones that it deemed were most important. SR4, we used the same queue. However, we found that while processing effects, the worker threads were not being used at all because our effect system was not multi-threaded. So there was a lot of processing power just not being utilized. So we pushed all of these raycasts to happen in the worker threads. And since we have more than one thread and we have more than one system that was not multi-threaded, we could effectively do 80 raycasts per frame instead of 4. And this was actually with a overall reduction to main thread processing time. So this was a huge win for us. This nightmare case before that took 15 seconds, we could now do in less than 1 second. And using some of the prioritization that we had before, this cuts it down to about 1/10 of a second. This gave us very good response times, even in worst case scenarios. And it actually pushed us to do more line of sight checks for acquiring cover positions, among other things. So the main takeaway here is that multi-threading your AI in any respect, you don't have to multi-thread the whole thing, just taking one piece of the expensive part and multi-threading that will give you huge wins. And also in doing that, you can reuse it for new purposes. Next, I'm going to talk about the architecture changes we went through to work with our scalability issues. So a long time ago, we used a finite state machine, and over 2 projects, it grew and grew into what we refer to as spaghetti code. It took nearly a day and a half to simply stub in a new behavior, not even write the code for it. Just to start writing the code for it took a very long time. This had huge overhead costs, and the dependencies in connecting your new behavior to any of the old behaviors was just a lot of unnecessary work, and it was really crippling our ability to prototype and test new behaviors. Also, with these dependencies, it created a lot more bugs that were harder and harder to track down. And the worst part about the finite state machine was that the more you add to it, the harder it is to work with it. So we started looking at new systems. We wanted something that was a little bit more efficient on the processor, but also on the developer and designer. Because of our history with finite state machines, they were no longer being considered. And because Saints Row is a large game, we were still concerned about performance. And Saints Row is a very volatile game. Things change a lot. Making long-term plans didn't seem like a viable option. So we didn't want to consider a planner. Also, we wanted the system to be deterministic because we don't tend to roll dice. We tend to rely on the player to be the most random variable in our game. So to kind of walk through what the system is, we were familiar with planners. We'd used planners. So it starts with a list of goals. And you go down the list of goals until you find one that is valid at that particular time. And each goal has a list of actions. So you go down that list of actions until you can find one that is viable at the time. And the first one's viable executes. And this kind of looks like a behavior tree, kind of looks like a planner. There were certain overlaps between the two. And the main advantage to this was that all of these lists of goals and actions were all data-driven. So the tree could be manipulated by programmers or designers very easily. Once our behavior tree got to a certain extent, it was too big and too complicated for some of our designers to use. So we tended to edit that just by programmers, but it still provided a certain efficiency that we did not get through code and finite state machines. The designers, however, were encouraged to create new profiles, new behavior sets that were subsets of goals and actions and had certain parameters for those goals and actions. This really became evident when one of our producers came to us and asked that we make Burt Reynolds a follower. And he can't use guns and he can't die for legal reasons. But thankfully, we already had melee behaviors and follow behaviors and invulnerability, and all those aspects had already been coded into data-driven methods. So it really only took about 5 minutes to set up the data for Burt Reynolds for his behavior. And to really kind of reiterate the wrong way to do this, if your code is saying, if Burt Reynolds, you're not doing data-driven properly. The Burt Reynolds is actually the sum of the parts. He is not one piece to be queried in multiple places in code, because that creates a lot of dependency and a lot of code that cannot be reused later on. To illustrate this another way, the warden, one of the most complicated characters that we iterated on the longest on Saints Row 4, he had 26 behaviors. And 13 of these were originally created for the Saints Row 3 cop. These behaviors did not change specifically for the warden. There were some fixes, but these were completely reused. And of the behaviors that we created for the warden, 10 of those were then reused for other AI types in the main game and in DLC. So that leaves 3 behaviors remain completely unique to the warden. My takeaway here is to try to increase your efficiency and to reduce your overhead as much as you can, because that will pay huge dividends in the long run. Our iteration time was greatly increased. We were able to iterate on the warden much longer and get a lot more progress done than we would have in the old system. So next I'm going to get into some topics on environmental interaction. This is about how to connect the player or the AI with their surroundings. And this can be difficult to do in a meaningful way in a very large city with a large set and a large scope. One of the simplest ways we did this was through action nodes. They have custom animations, props, VO, and these kind of animate the players and connect them to the world in very different ways. And they can also kind of reinforce or sell the environment or the story of what's happening. And it's also very beneficial to ground the player after he has done something absolutely ridiculous. Hundreds and hundreds of these were placed across the city, and that's actually what I want to get at, was that the amount of time we spent man-weeks putting in over 500 action nodes across the city, and even more in interiors. So really don't underestimate how much time or the amount of effort that goes into populating a city. However, there are some good tricks we can do. One of those is to reuse your markup. One of the best systems we had was procedural roadblocks. These would take existing road data that was all across the city and could fit a set of enemies set up in a roadblock across the road. And we had sets of these for 2, 3, and 4 lane roads. And because this code used existing data, once it worked, it instantly worked across the entire city. It was extremely scalable. So, to reiterate, reuse your markup where you can. However, there's a catch to this that can be pretty risky. Here we have an example of a brute attempting to pick up a propane tank to throw it at an enemy. However, we didn't want to have to go and add tags to every prop in the world to say where brute should pick them up. So there's an algorithm that does some raycasting to figure out what point on the object the brute should pick it up. And this picture here is actually from a bug report saying that the collision data on the propane tank is too inaccurate for this purpose. And that's actually kind of the point that I want to get at here, is that if you're reusing data for a different purpose than it was initially authored for, then you might run into a lot of bugs, or you might be making some assumptions that aren't safe to make. So you will have to go back and correct that data to work for both purposes. And that will take some time. So it is not always free. Saints Row 4, we had another problem where we reused the city in a new way that we had not used in the past. So now the player can run up walls and jump over buildings. And the primary problem was now he had access to all the rooftops. And there was no nav mesh on rooftops. So how do we have AI follow and engage the player on rooftops where there is no markup data? There wasn't originally intended to be gameplay in that area. One of the ways we addressed this was the new jumping behavior. This leveraged the raycasting optimizations that I talked about earlier. And the way this works was we did a lot of raycast down from the sky. And this would find where it hit the ground, where it hit rooftops, where it hit awnings, all sorts of geometry, wherever we could land. And then it would do multiple raycast from the start location to all the possible destinations. And it would be running heuristics on this on each pass to figure out what the best locations to jump to is. And then it would pick one and it would jump there. Here's an example of it in game, and we actually have an enemy jumping from a rooftop down to the ground to get closer and to get line of sight to the player. And this was intended initially implemented only for the wardens to use. And so we weren't really considering performance. However, then we needed homies to be able to follow the player onto rooftops. And then we needed specialists to follow players on rooftops. And then it kind of caught fire. Designers liked this behavior so much that we ended up putting it on probably half of the AI types in Saints Row. And there were some performance issues, but we were usually able to just throttle this behavior so that too many people weren't doing it at once. And that avoided that issue. The second technique we used to account for no nav mesh on rooftops was to fly. And we didn't have markup for flying either. We didn't have voxels. We didn't have any really pre-baked spatial analysis. So we started with just your basic avoidance algorithm to not run into buildings, not run into cars. And this leveraged the raycasting optimizations as well, because it would need to do these every frame so that it could have good reaction times when it's flying through the city at 50 miles an hour. However, there's always the problem of, well, what about the U-shape? How do you get unstuck from a particular location? And it didn't take long to kind of figure out a new way to do this without nav mesh. And it's a little heavy-handed, but what we did was a raycast away from the player every frame. And these raycasts would be cached, and what the AI would do was when they detected they were stuck, they were in a U-shape, or they hadn't made any forward progress, they would query these raycasts to find one that is further away than they were, but in their same direction. So in this particular case, they knew they could go. Oh, that didn't work. They knew that they could go to where that raycast was and then have line of sight to the player. And this typically got them unstuck. It didn't always work, but it worked most of the time. And when it didn't work, usually the AI was stuck in a location where they couldn't see you and you couldn't see them, and it wasn't noticeable to the player. And typically there was enough other enemies around that one missing was not a big deal. So we were able to squeeze by with that one. Here's an example of the flying AI going through a tunnel. And this was actually really beneficial to us because our previous flying AI, our helicopter AI, ran off of height nav mesh, or height mesh, and it did not, it would not be able to run through a tunnel or a tight interior or a space with lots of catwalks and complex geometry. However, these were fast and nimble and responsive enough that they could get into basically any tight space. I do consider these methods to be high risk, high reward development because there's a lot of bugs with it, but once it does work, it works across the entire game with very little markup, very little maintenance. So there are pros and cons to doing these. So to wrap it up here, I wanted to kind of tell you about providing a good pacing with your open world content and to make your AI more efficient, but also making your developer more efficient because the scope of these games is really big. And also to adapt new ways to use markup data for new purposes. I think that's a really big win for us. Thank you for listening, and I will send out my email so that you guys can contact me personally. Thank you.